Welcome to Lecture 4 on the topic of modern food production, knowledge and technology. This lecture is the fourth lecture in the subject of food production in a changing world, which is a component of the Bachelor of Agriculture and Technology. This is offered at both North Melbourne Institute of TAFE and Melbourne Polytechnic. Please visit our website www.nmit.edu.au for information on this course and other courses that we offer. My name is Dr. Nikki Cooley. In this lecture we will be covering two learning outcomes for this subject. The first is to understand how the drivers of change in contemporary food production systems have been aided by advances in knowledge and technology. The second, which we will explore in part, will be learning about the changes in knowledge and technology through the Australian perspective. So let us look at a selection of the very first and early agricultural innovations. In about 12,000 BC, the Natufians in the Levant area began harvesting wild grasses. This development allowed the establishment of permanent settlements and was just on the cusp of farming as we know it today. The production driver here was two aspects. It was knowledge and the ability to harvest the wild grasses. These people continued to be innovative and gained knowledge. They were then noted as the first peoples in humanity to farm pre-domesticated crops. This is where they took wild barley or wild oats and farmed them. The production driver here was the ability of the farmer to farm pre-domesticated crops. This was the start of farming. Another innovation that these people came up with in this time was the ability to store. This again would have been a significant production driver. This innovation should not be underestimated. There is a suite of knowledge that we take for granted about growing plants nowadays that we just simply did not have back then. We had to understand that plants required light, required water, and required nutrients. And while these early farmers did not really understand what nutrients were, they certainly did understand and observe that muddy water, which we now know is full of nutrients, gave the best results for productivity. The next significant innovation for agriculture was the cultivation of wild grasses. There are a suite of these that were cultivated over time. It is generally accepted that the first farmers in Europe grew crops that had been cultivated in the Near East, which happened about 2,000 years before reaching the shores and inland plains of Greece. Plant remains from early Neolithic sites indicate that the earliest farming villages, dating to about 6,700 years before Christ, grew a number of kinds of wheat, emmer and einkorn and bread wheat, two-row barley, lentils, bitter vetch, peas and flax. I'd like us now to concentrate on the cultivation and look at this in a bit more detail. We can follow approximations of individual species and see approximately when they developed. Accurate records of these times, of course, are difficult to come by. Einkorn wheat is the wild propagator is Triticum monococcum. What we mean there is that the wild species is the Triticum, which was cultivated into Einkorn wheat. This happened about 7,400 to 7,000 years before Christ. It's widespread today. It grows on rocky, dry soils and is hardier than many other species of wheat. The earliest certain remains of domestication of Einkorn wheat can be found in southern eastern Turkey. This variety is not as common as Emmer wheat, but it is present in small quantities in the earliest farming sites. Moving on to Emmer wheat. The wild propagator of this variety is Triticum turgidum. It was found in modern southern Levant, southeast Turkey, and the Zagros Mountains. It grows in oak park forests and steeple forest on basalt and lime soil. The wild species of this wheat has been recovered from Israel, dated to 19,000 years ago. It remains one of the earliest predominant sites in Europe for domesticated cereal. Bread wheat is another variety, and this can be distinguished by an examination of the spikelet remains. Such remnants are not often preserved on the archaeological sites in quantities sufficient to facilitate the distinction. However, it is recognised that this either comes from Triticum abscisium or Triticum durium, probably the latter. The first clear evidence of this came about 6,800 to 6,400 years before Christ. It appears in different countries at different times. It is an important development in the processing of wheat. Barley is a very tough plant and usually thought of as a bit tougher than wheat. This was first domesticated about 7,700 BC. It has both a hold and a what's called naked variety, and that is how the wheat head looks. The grain head looks, sorry. The wild propagator of the two-row hold barley, the earliest domesticated type, comes from Hordeum spontaneum. It is fairly well spread in what is called the Fertile Crescent, that is, the Levant and the footholds of Cyrus and Zagros Mountains. Genetic data suggests that barley may have been domesticated in two areas in the Near East. A possible form of domestication may have occurred in the Tel Aswad about 7,700 BC. Rye, a cereal crop, was thought to have been initially domesticated in Europe, where it is now a important modern crop. There is some evidence, however, to suggest that it was first domesticated in the Near East. The wild propagator of domesticated rye is the species Sisal cereal, and it grows in fairly dense strands on the lower slopes of Mount Ararat in eastern Turkey and south-central Turkey, which border with Syria. And finally, touching on the legumes, the first legumes thought to be domesticated were lentils, peas, and bitter vetch. This was followed shortly by chickpeas, and they are all amongst the earliest legumes to be domesticated, and this was believed to occur in the Near East. But they are not seen commonly until the late Neolithic era in Greece. The principal difference between wild and domesticated legumes, as with the cereals, is their ability to propagate their own seeds. This held farmers back. The pods of wild legumes are subject to drying out, and they can split upon ripening, where the seeds will dry and scatter. In domesticated legumes, the pods have been altered so that they open only when they are mature. That is, when the pea or the lentil is ready to eat. This again is a significant advancement or driver which enabled farming of this crop. So now let's have a look at a selection of very early ancient tools which enabled farming. The first tool I'm going to show you was uncovered in Sweden, and it is an axe made of granite. There was more commonly used flint tools just before this period. The stone axe, however, enables a way of cutting down forests so that crops could be grown in their place and pastures could be grown to allow animals to graze. Therefore, the production driver of this tool was that it allowed for land clearance, which enabled larger scale farming. This tool dates to the northwest European Neolithic, the period when societies across northern Europe began to adopt agriculture. The transition from the hunter-gatherer societies towards a more settled, farm-orientated existence, as stated in Lecture 2, is one of the most critical movements in human history, and this tool went a long way to enabling civilization. Another of the first tools which enabled agriculture was made from clay structures. The image on the slide shows an example of this and is termed a harvest sickle. It does what the name suggests, that is, it allows the harvesting of grain from early crops. This was done by hand. The production driver for this is that it enables the harvesting of the crop. This strange looking image, which looks more like a football than a tool, is actually a cereal grinder tool. Its innovation came about between 3000 and 2000 years before Christ. It is a tool that aided the separation of the husk and the grain in the preparation of grains. This is again an important production driver, as it allowed more efficient processing of the product. Taking a bit of a jump now, we are going to move to about 1550 to 1069 years before Christ, in the first introduction of wooden farming tools. The image on the slide shows a collection of wooden farming tools where innovation occurred around this period. This image was sourced from the British Museum collection. Neolithic farmers used wooden planks that were arranged and tied to oxen to create movable ploughing systems, and that preparation of the soil and the sowing more efficient and easy. These were the first ploughs, and that was the driver. It enabled harvesting. At the time, cultivation along the banks of the Lower Nile brought new technologies and innovation practices. Farmers used these advanced tools, such as the handheld plough and another tool called the flail, to aid mass cultivation. This takes you from feeding a family or small village to a much larger collection of people. The hand plough and the flail were so important to the people at the time, they became sacred symbols of leadership. One of the earliest known pre-dynastic sultans, Scorpion, was depicted holding the hand plough on the mace head. This was documented in southern Egypt about 3002 years before Christ. Another innovation I want to look at is that of crop rotation. The issue that the industry had before crop rotation was that a decrease in soil fertility was seen, and in some cases soil diseases could be impossible to control if the same crop was grown in the same location year on year. Different areas have taken up this innovation at different times. For example, crop rotation was first practiced in ancient Roma Africa and Asian cultures. During the Middle Ages, it was taken up in Europe, where a 3-year crop rotation was practiced by farmers, where they rotated rye or winter wheat in one year and followed by spring oats or barley in the second, and in the third year they would have a year where they would not plant anything. This led to massive increases in efficiency and productivity. It also, but by increasing soil fertility and the control of some diseases. In the 18th century, the British agriculturalist Charles Townshend aided the European agricultural revolution by popularising a 4-year crop rotation of wheat, barley, turnips and clover. In the US, George Washington Carver brought his science of crop rotation to farmers and saved the farmers' resources of the South. Now looking at innovation through colonial times, one of the most important instrumentations, which was very industry specific, was an innovation by Earl Whitney of what is called the cotton gin. This occurred in 1793. The problem at the time was cotton was expensive due to the difficulties with separating the seed from the fibres. The invention of this machine consisted of a row of close-set wheels and saw-like teeth around their parameters. The wheels protruded through the narrow slits between the metal bars into a hopper filled with cotton balls. As the wheels turned around, the teeth caught the cotton fibres and pulled them through the slits, which were too narrow for the seeds to pass, thus separating the two products. The Whitney's cotton gin allowed the processing of 453 kilograms of cotton in the time it used to take 1 man to process 2 kilograms of cotton by hand. This was a significant production driver. It increased the processing time and efficiency of cotton production. There were consequences of this, perhaps unseen at the time. It resulted in a significant reduction in the price of cotton. That is because a large amount of cotton could then be processed. There was then more cotton on the market. Basic supply and demand characteristics came into play, and the price fell. A not so popular consequence of this is that more slave labour was required in order to keep the cotton plantation productive. Thus, the invention of this machine unwittingly resulted in the entrenchment of slave labour in the South US at the time. Another innovation I wish to talk about is the innovation of the British Agricultural Revolution, which started about the 1750s and went through to the 1850s. This was an example of innovation that brought together many changes. There was improvements in crop rotation, the introduction of the Dutch plough, enclosure, development of a national market, transportation, infrastructure, land conversions, drainage and reclamation of land, a rise in capitalist farmers, and significant improvements in selective breedings, and therefore crop productivity increased. There were several impacts to these changes. There was an increase in the UK population, and the driver led to increases in labour and land productivity. I will go into some of the innovations which enabled this change in the next few slides. Another invention in the colonial period was that of the reaper and binder in the 1830s. The industry had an issue at the time that hand harvesting of grapes was time-consuming and resulted in poor efficiencies. A reaper is a farming tool that reaps. Therefore, it used to cut and gather the crops at harvest. As you can imagine, the production driver of change here was that there were quicker harvesting times and reduced labour input. This invention was accredited for a significant reduction in the price of bread. It has an interesting history. Towards the end of the 18th century brought us to the innovation of the steam engines. This allowed the production of new farm machines that did not require as much hard physical input by the farmer, labourer or slave. Initially the power requirements for these machines were topped up by either an oxen, a horse or a mule. The first steam engines were stationary and used to run cotton gins and mills. The additional power required improved threshold machines, which then led to the development of portable steam power. This first made an appearance in 1849. It was during the 1870s when a significant development occurred as the practical drive systems and the self-propelled steam traction engine was commissioned. These machines were able to pull multiple gang ploughs in the large fields of the wheat belt. Therefore, this innovation reduced significantly the amount of physical labour that was required in the farm industries. Physical labour is timely, it's difficult, and it adds expenses to the industry. This innovation produced a significant driver of change in that it enabled a larger area of farmland to be farmed. This changed the industry supply capabilities. The innovation of the general purpose tractor in the 1920s is the next significant stage in mechanisation that I wish to talk to you about today. Firstly, please note that the gasoline tractor superseded the steam tractors sometime before this. The issues with steam tractors were that they required a lot of water and fuel in the form of coal or wood or straw. And they also required a trained engineer to drive them. It was the use of gasoline that enabled the internal combustion engine to be developed in the 1890s, and this offered an important step and alternative to steam. The first commercially successful tractor was built in the Charles City, Iowa by Charles Hart and Charles Parr. Early tractors were big, heavy, awkward, and none too reliable, but by the 1920s the better ones had survived and were becoming more popular in American farming. They enabled the heavy tillage and belt work that was required at this time. These developments led to the innovation of the general purpose tractor, which occurred during the 1920s. Row crop work such as planting and cultivation was still largely done by horses, as tractors were too heavy and not versatile enough for these lighter jobs. Several lightweight row crop tractors had been tried, but most were not satisfactory. Several manufacturers offered motor experiences for the teams, but a few farmers were willing to buy a machine that was used only a month or two. In 1924, the IH was introduced by Farmwell. This was the first general purpose tractor that could pull heavy tillage and harvesting machines, as well as the plant and cultivation rows. The image on your screen is a later version of this, the K3 type engine, which was used by the Japanese in 1945. The driver of change that enabled with this innovation was improved efficiencies, increased diversity to mechanisation of jobs, that is, more jobs could be done, and changes to economical outputs. This increased the capabilities to the supply chain. Rubber tyres came on the scene in about 1928. The previous tyres that had been used had limited speed and were often subject to extreme vibrations. This limited the functional abilities of the general purpose tractor. Therefore, with the introduction of large-scale commercial rubber tiles, the innovation for change was improved efficiencies of the machines and the potential of more delicate type farming operations. And the final innovation I'm going to talk about with respect to mechanisation is the innovation of the hydraulic implant, lift and draft control systems in about 1927. The issues were the earlier tractors had difficulties with their lift capabilities, both in the flexibility or what they could lift and the total amount of weights that could be lifted. This innovation changed this. It led to improved efficiencies and improved versatilities of farming operations. Please read the following resource on agricultural machinery. This will give you an overview on agricultural machinery. Read the article and add to your lecture notes here, please. In this slide, we're going to look at how the scientific model may or may not have influenced neutral efficiency increases in farming across the 20th century. So there is evidence to show that global food production increased across the 20th century. And one might ask, why was this increase? This increase was evidenced in particular by wheat and rice world production. So there is some evidence to show that the scientific model is responsible for how technological innovations tended to be introduced in agricultural production systems during the 20th century. Please note that observations recorded in the 20th century are quite different from those found in the 21st century. For example, the Asian rice-producing regions evidence an acceleration of technological process that is similar to that of the world's pattern in the 20th century, and thus supports the theory. However, there is a lot of evidence across this time, across many regions, that does not support this theory at this time. In fact, it is hypothesized that it is a population driver that drove neutral efficiency of farming increases rather than technology in the 20th century. There were significant changes between the 20th century and the 21st century in farming, innovation and technology. These advancements can be seen by increases in neutral efficiency of farming in the 21st century compared to those in the 20th century. The reasons for these changes also change. There is more support for the role of the scientific model as a driver for neutral efficiency of farming. At this time, there has been a significant change to how information is communicated across the globe. That is, in the 21st century, information is freely available by mechanisms that weren't available during the 20th century. Therefore, the scientific model is seen as a significant input or driver for neutral increases in efficiency of farming in the 21st century. One of the most significant modern-day innovations has to be that of the Green Revolution. This started in the 1940s and went through to the 1960s. In order to realise why there was a need for the Green Revolution, you have to take a step back in time. At the beginning of the Green Revolution, it was realised how low crop productivity was, particularly in some areas of the world, like some of the developing countries such as India. It was a real issue. World population was growing, and there were significant issues of hunger, and when this was mapped against population growth, there was much concern in the community and in politics about predicted food shortages. There was a great amount of fear at the time. At this time, another thing changed. Scientists and industry representatives of agriculture started working closely together. Governments, such as the UK and the US, were handing out grants and money for a combination for these people to work together. And it is indeed the combination of a number of technologies, not just one single technology, which led to this innovation. These technologies included being able to manipulate the plant on a new level. One of them is the semi-dwarf rice variety. Along with the manipulation of plants, there was improved fertilizer use efficiency and improved water use efficiency that had never been seen before. Therefore, the result of the Green Revolution was a step change improvement in crop productivity. This was a significant driver to the industry at the time. You may think of this one as a strange one to include, the shopping trolley, but it is actually a very large driver of change in modern agriculture. One of the first shopping carts was introduced on the June 4th in 1937 and was an innovation by Goldman. Goldman owned the Piggy Wiggy supermarket chain in Oklahoma City at the time. One night in 1936, he was sitting in his office wondering how customers might move more groceries. He found a wooden folding chair and put a basket on the seat and wheels on the legs. Goldman and one of his employees, Fred Young, a mechanic, began tinkering. Their first shopping cart was a metal frame that held 2 wire baskets. Since they were inspired by the folding chair, Goldman called his carts folding basket carriers. And so the inventions continued until you get to what we now know as the modern day shopping trolley. This has enabled a large collection of the transport of food, of groceries, that is, within the store and to the mode of transport, usually our car. This enabled the takeoff of the supermarket, and the supermarket has undoubtedly been a significant driver of change, both from a consumer perspective and from a productive perspective. On the screen on the right hand side you will see the original patent documents showing the design of the nested features of the telescoped cart, or as we call it now, shopping trolley. The next area of innovations I want to talk about is that of the sensing networks and sensing revolution. This is huge. We are now able to competently and quite cheaply monitor soil, water, climate, some plant growth, some plant diseases, some animal health aspects, milk production, and so the list continues to grow. The figure on the screen shows an image of a wireless network. It is a combination of wired or wireless radio signals that enable us to use this information in a production system. This again has caused a stepwise increase in productivity. An example of a plant sensing component that's made a big difference is our ability to monitor chlorophyll. Chlorophyll meters are promising as they can be correlated to nitrogen management. Crop nitrogen status can be established using a chlorophyll meter, and since most of the nitrogen in the plant system is contained in the Rubisco enzyme found in chloroplasts and chlorophyll proteins, there is a close relationship between leaf nitrogen and leaf chlorophyll content. Therefore, you can apply fertilizer optimally and you can get very good returns. That is, very good increased fertilizer use efficiencies. With the innovations of sensing comes a natural progression, which is precision agriculture. Precision agriculture is the integration of new technologies, which include GIS, GPS and RS, to allow farm producers to manage within field variability to maximise the cost-benefit ratio of their system. Variable rate technology, another significant innovation, available with farm implementation instruments, can be coupled with tractors to deliver optimal levels of fertilizer and CCP applicators, along with yield monitors. All of this has evolved rapidly and has focused on the growth of the precision agricultural industry. This industry is in its infancy. However, it does show the potential for a step change improvement in crop management and productivity. The next innovation I want to touch on is that of computation and modelling. You can now do in-season predictions of crop yield potential using models, for example cereals. This technique offers possibility for real-time nutrient and water management, and also allows you to know what amount of inputs you should put in the field, because you can predict your yield, which enables you to make economic assessments of your crop. Many of these models are based on a quantitative understanding of underlying processes and integrate the effects of soil, water, crop, pests, and management factors on growth and yield. Again, this particular innovation, as I see it, is in its early days. and has a great potential for step change improvement in crop productivity where these resources and knowledge are available. Another important innovation to mention about the 21st century is our ability to breed and use molecular biological tools to improve our breeding and breeding programs. This innovation base is wide, and to talk about it comprehensively here would take too much time. However, from a one-statement perspective, we can sum it up in that many of these techniques are being utilised together to significantly increase the time of breeding programs, which ensures new innovations come from this. This is an example where both industry and its requirements need to work alongside science and its technology to get the ideal product. Some of the techniques that are included in this technology are advancements in tissue culture, identifying useful genes and then being able to put these useful genes into the organism that we require. We can do this in both crop and animal species if we choose to do so. This has the potential to cause step change improvements in crop and animal productivity, although we were probably on an early stage of this particular innovation. In the recent years, there have been many examples of how knowledge and innovation have come together to be drivers of change in agriculture. Here is just one example. Cyrus scientists in 1977 developed a water-soluble polyethylene pre-polymer. This is a technology which enables wool to stop shrinking. This is important because the Australian industry can only compete internationally if it has an edge. That is because the cost of production here. Therefore, it really does have to rely on technology. This particular innovation enabled a higher quality. Thus, Australia could continue and to improve its international exports in the fine wool markets. There is a phrase that goes, if you cannot measure it, you cannot manage it. And I believe this is very true for farming. In this next couple of slides, I want to touch on some of the most recent innovations. Many of these innovations will be covered in the degree subject Future Farming Technologies, and as a result I'm not going to go into any details about these innovations, but rather touch on how they are leading change. I'm going to start with resource sensing. This field has significantly increased in recent years. It has and will continue to enable efficiencies in water use, efficiencies in fertilizer application, efficiencies in herbicide and pesticide use. There are several drivers of change. The most significant is probably the increased economic viability of farming. But also, if you remember our previous lecture when we were talking about sustainability, resource sensing plays a great role in the driver for improving farming sustainability. The invention of satellites and enabling global positioning systems, or GPS, has enabled automation of machinery and accurate monitoring of resources. This will continue to improve. The driver for this is increased economic viability of farming. Just touching on communication, in the last few years this has made significant advances. Nearly all modern day farmers have iPhones or access to the internet. This has allowed significant drivers of change. Most of this has occurred around the accessibility of knowledge, but has also enabled more efficient, real-time, dynamic resource sensing and communication of information and data on appropriate spatial and temporal scale. And finally, perhaps one of the most exciting areas brings together many of these innovations into increasing whole farm viability and resource efficiencies, and that is of precision agriculture. This is still really in its early days, and it tends to be industries of large scale where there is a high prevalence of technical knowledge. However, with the innovations of software and improved use and farmers becoming more used to seeing this kind of data and learning how to interpret it, there is massive potential for increased productivity and savings for the future in farming. A few things to realise when you are thinking about modern innovation and technology drivers of change. 1. Infrastructure is often required in these new innovation and technologies. In the case of resource sensing, communication use, GPS and precision agriculture, infrastructure is essential. Knowledge is also essential to resource sensing, communication use, GPS and precision ag, and other components of the industry as well. Farm management software has increased in its capabilities recently and will continue to do so. The aim of this software would be to include reliable early predictions, reliable early detections, and forecasting capabilities that enable you in every part of your farm management. The drivers of change of all of these are increased efficiencies to the agricultural industry, improved probability of dealing with climate change implications, and ultimately improved economic return for the industry, resulting in some long-term viability. I want to briefly touch on the role of technology and knowledge transfer. This may be obvious, but some technology and/or knowledge can be transferred to any farming region in the world and will result in efficiency production gains. However, there is some technology and knowledge that cannot be transferred to any farming region. A technological advancement in a developed country may require infrastructure not available in a developing country. An example of this is you may look to introduce harvest mechanization to increase your productivity in remote areas in Indonesia. But this may not be possible if you consider the poor road infrastructure and unreliable fuel supply that can result in these areas. Advances in knowledge transfer and how they relate to agricultural production systems has been significantly aided by other technological advances. For example, telecommunications has increased in the 21st century in a way it just has not been seen previously. There is more telecommunications, more accessible in remote regions, including some regions of Australia, where telecommunications can be quite reliable by satellite infrastructure if you forgive the price. There are many areas in the world now that have reliable telecommunications which aid their agricultural practices. There is global infrastructure to support these phone networks. It should be noted that there are still some areas of the world where telecommunications technology is not up to speed and it is not as reliable and perhaps inhibitory from an expense perspective. This obviously leads us to the next advancement, the Internet. For a brief snapshot of some 2012 Internet usage statistics, you can refer to the Internet World Stats. These statistics are impressive. There are many people able to access the Internet now. There have been significant advances to computation, both in the reduction of costs of computers and in what you get for your money. There is information available to global markets about production systems all over the world. This has enabled real-time dynamic changes in prices that can respond to actually what's happening across the global market in a way that just wasn't able in the 20th century. There have been advancements to manufacturing. That is, many parts and infrastructure can be made much cheaply, much more reliably, which have also aided knowledge and agricultural production systems and information transfer. And finally, there has been advances to science, both in molecular engineering, modelling and nanotechnology, to mention but a few. I have put together the following resource for your information and to complement this lecture. Please note this is essential reading. The following article, Adaptation of Knowledge Systems to Changes in Agriculture and Society, the Case of the Netherlands, can be found on the internet via the following URL link. Please read this abstract and make some notes. It is a perspective of agricultural adaptation and knowledge systems. It describes the systems that are currently in place in the Netherlands, both research and educational, and the challenges that both the industry and these systems face. It is perhaps a not unexpected outcome that the ability to adopt to change is the most important factor in agricultural systems and efficiencies. It is the adaptation of knowledge systems that enable the ability to adopt to change. So what are the key points that you need to take away from this lecture? Well, you should be able to now describe some of the important technological advances that have occurred in agriculture. This lecture is not meant as a definitive resource, but rather listing some of the many important examples that we have come across. You should be able to describe the role of mechanisation, as this is a significant component of agricultural advancement, and give a few examples around mechanisation. You should be able to describe advances that have occurred in both the 20th and the 21st century, and link these advances to how the production system has improved in efficiency. And finally, you should be able to describe the role of some key supporting technologies, such as that of communications. This brings us to the end of this lecture.